So hello everyone, my name is Marco Fellous-Asiani and I will present to you this perspective which is still in preparation. We're currently writing with the following authors, some of which are at this conference. And so let's begin. So it's a perspective on the energetic challenge of fault-tolerant quantum computing. And so first, why should we care about the question? So the first reason is a reason of technical feasibility. If you have quantum computers that have a power consumption that far exceed what the electrical grid can provide, it will be an issue for the very feasibility. So that's the first question. The second question is related to the operational cost to operate the device. So imagine you have two companies which sell you quantum computers which are able to reach similar computational performance, but with one of them having an energy consumption to solve a given algorithm that is 1,000 times less than the other. Basically, the company that consumes too much energy will lose in the competition. So it will die for economic reasons. So that's a second reason. And of course, the third one is the question of environmental footprint of the field and societal acceptability. And so why should we care now about this question is because we are at the roadmap era. So it's the moment where we have to think about this problem, because once you deploy a technology at scale, it's extremely difficult to fix this issue afterwards when everything has been designed. So here I will give some number about what we currently know or can infer for power consumption of useful fault-tolerant quantum computer able to solve problems of typical sizes. So first there is the psi-quantum. So what we know, but there is a caveat I will say just after, is that our quantum computer could consume about more than 100 megawatts of electrical power. So the way we know this number, it's not publicly directly said by psi-quantum, but you can see it's publicly accessible, an electric contract they made to the electrical grid provider to power the facility where they will build their quantum computer. And if you know the largest classical supercomputer in the world, they can consume 10th of megawatt. So you see it's really a lot, this psi-quantum. And then you have some startups that claim that they could go below 100 kilowatt or less. So what you see is that there is basically a huge uncertainty. The power consumption can either be huge, either can be very reasonable. So we don't exactly know. And basically, these numbers are either directly said publicly by the company or we can infer them. But the thing is that there is no peer-reviewed paper on that. So we are not yet at the level of realistic estimate. And so the realistic number, it's possible they could even be larger. So first, let's understand the problem by where is energy consumed in a quantum computer. So the energy is not only consumed by the hardware during the circuits. So essentially, you have two things. You first have a classical computation in parallel of your quantum circuits. And your energy is consumed even before the circuit starts. So for instance, before the quantum circuit, you have to compile or optimize the circuit that will actually run on the hardware through classical software, and it costs energy. Then you have the quantum computation occurring, and in parallel, you have classical computation that occur, for instance, to manage error correction. So I'm just giving an example. I will not be exhaustive here because it will be too long. And after the quantum circuit is run, you might have some post-processing from the measurement of the qubit to deduce the answer to the computation you want to solve. And you, of course, have the hardware control. And even there, stuff can occur before. For instance, gate calibration, which costs energy. And then during the computation, you have to prepare your qubit, drive them with laser, microwave, and so on, and it consumes energy. And many of these things, actually, they will be multiplied for at least two reasons. So the first one is cryogenics. So as you might know, in many modalities of quantum computer, you have a cryogenic unit to keep your qubit cold to prevent noise. And inside of the cryogenic, you might have some electronics, for instance, to drive your qubit that might be inside. And so you have two things. You have to give energy to your electronic to control the qubits. And this electronic will dissipate this energy into heat that needs to be removed with the cryogenic, which is an additional cost. So you multiply the cost, essentially. And you also have quantum error correction. So when you do error correction, each of the logical qubits you really need in the algorithm is encoded in, let's say, 100 to 1,000 physical qubits. So it will multiply many of the costs here. So now a question that is good to understand is why is the hardware's consumption so high, given the fact that the transition energy of the qubit is so tiny? It looks a bit crazy, right? So let's try to understand this. So here I will explain this with an example, but this example is very illustrative because it can help understanding many platforms. So let's look at how we do a single qubit gate on superconducting qubits. So what you do is essentially you have some electronics that will generate high fidelity signal, and you first have to spend energy there. So then you create a signal that is the one that will be used to drive your qubit. And then this signal, it goes down and will go in an attenuator, which was just presented in the previous talk. And so basically, the reason we put this attenuator is that so it will dissipate most of the signal at its input and dissipate it into heat, which will need to be removed because this attenuator is inside a cryogenic unit. So you also spend energy to remove this heat. And why do you need this attenuator? So to put it simply, it was already explained in the previous talk, but it's to allow a high signal over noise ratio that reach your qubit. Otherwise, your signal will be too noisy because your electronics there produce noise, and it allows you to isolate from the noise this electronic produces. And then your signal interacts with the qubits, and the signal amplitude is actually for fundamental reason much larger than the energy transition of your qubit. Otherwise, you will introduce decoherence. And this pulse is typically dissipated afterward. And here you have what I will call the quantum scale cost. So it's not necessarily exactly h bar omega, because this pulse can still be much bigger than h bar omega, but it's still very small compared to the classical scale. And here you have the classical scale, which is macroscopic. So here is what you can really measure in the lab. It's the big part of the cost. And the first message we can understand is that essentially the reason why the consumption is so large is because we have to fight for noise. If there were no noise in quantum computation, we will not need high fidelity signal generator that consume a lot of energy. We will not need to have a cryogenic system because the qubit could be at room temperature. We will not need to have attenuator, and so everything will drastically go down, and in practice your costs will be completely negligible from a classical perspective. So you have your quantum scale that is really tiny, and the classical scale is amplified by many orders of magnitude, and this coefficient here is essentially here because you have to fight noise. If you did not have noise, your energy cost will be almost zero. The second message I would like to give is that it's not always the case, but in some architecture, actually, a significant part of the classical consumption can be directly proportional to what you consume at the quantum scale. So I'm not saying it's always the case. I say in some case it can be possible. And this is related to the second message I would like to give. If you want to make a fair total estimate of the energy consumption of your quantum computer, you need in general to know how much you consume at the quantum scale, because the argument that it is tiny is not a good argument, because you take something tiny multiplied by a huge coefficient, and it can give something macroscopic at the end. And so here I can mention some related open questions to that. So the first is that for this architecture where we have a significant part of the classical consumption that can be proportional to the quantum one, it means that improving the energy efficiency at the tiny quantum scale, so at the level of, let's say, fundamental quantum physics, can in some case have an important impact on the energy consumption of large-scale quantum computers. And so the first challenge is to identify the architecture and the qubit modality in which it will be the case. And then, for this architecture, find a way to improve the energy efficiency of the quantum control at the quantum scale. And that's, I think, a nice example where you can see where fundamental quantum research can have a practical implication on the energy scalability of fault-tolerant quantum computers. The second message I would like to give is that estimating the total consumption is not a question of soul engineering, because at the very least you need to understand well how your noise is at the quantum scale, because it gives you access to this magnification factor from the quantum to the classical scale. And in some case where the classical consumption is directly proportional to the quantum one, you also need to know the energy flow at the quantum scale. So that's the second message here. Okay, so now an argument could be to say, okay, but maybe let's say I'm an engineer and I want to do an energy estimate of my quantum computer. After all, maybe I can say, I don't care about the details of quantum physics. I just discussed with a physicist. He tells me his fixed characteristic for his qubits, its power consumption, the parameter that influenced its noise. For instance, okay, he tells me, oh, the temperature is important. And he considered the qubit as a black box with fixed parameter, and he completely ignored the details of the physics. And then he does engineering work. He knows the characteristic his qubit should have, and so he designed all the computer and can estimate the total consumption. So this would work, but it's not optimal. You can do better by opening this black box, by including quantum mechanical model of the qubit to make a more accurate estimate. So this is what I will explain now. But for this, I need to define what I mean by optimizing energy consumption. So it means reducing the energy consumption, but while keeping the computation performance at least as good. Otherwise, it doesn't make any sense. As I said, if we are okay to have a lot of noise, I could make my computer basically spend a tiny amount of energy. So we really need to have this constraint here. And in general, the performance, they can be quantified by many things, the speed of the computation, but here we'll focus on accuracy, even though many of the things I say could also apply for time, because having a high accuracy for a quantum computation is the thing that is typically difficult. So okay, so we have, let's say, our quantum computation that is noisy, and as I said, the reason we spend energy is essentially to keep this noise under control. And we do this, for instance, so by spending energy in cryogenics, error correction, or high-fidelity qubit control. And so if we did not care about noise, the energy cost will, for practical purpose, be really small. And then there are actually two kinds of energy optimization you can do. The first one is what I will call reductionist energy optimization. So those are optimization where you optimize a single component. By component, I mean one of these orange boxes, so you could have more, of course, that's just examples, but without changing anything else in the computer. What do I mean by that? You optimize this component so that you reduce its consumption, but it does not impact anything else. And in particular, you do not change the accuracy of your computation. So you do not modify the performance of the computation. And you do not modify the energy efficiency of the other components. And in particular, because you don't change the computation accuracy, it means you do not change the physics of the qubits. There is no change in qubit physics, in their dynamics. So an example for that will be, I improve the energy efficiency of my cryogenics to remove heat. So if I do this, in many cases, it can be done in a manner that you will have, not necessarily, but it can often be done in a manner, it will have no influence on the noise experienced by the qubits, and it will have no influence on how error correction or high-fidelity qubit control will be done. And so you will just improve the energy efficiency of your cryogenic while keeping everything else the same, so you improve the energy efficiency of your computation. And there are cases which I will call holistic energy optimization. So those are the cases where when you optimize the consumption by optimizing how one component works in a manner that to not impact, to not reduce the accuracy, to not lose in performance, you have to change something else. And typically, this kind of optimization will change the physics of the qubits. So you have to go beyond black box model. You have to understand the physics of your qubit to do this in general. So an example is to put the qubit at hotter temperature. Because if your qubit is hotter, well, your cryogenic will spend less energy to remove the heat because it's easier to remove heat at hotter temperature. But you cannot only do this because then your dynamic will be more noisy. So you need to compensate it by doing something else. And an example is to compensate by doing more quantum error correction. So by having more physical qubit per logical qubit. So your qubit were noisier, so you spent less energy per qubit because you are warmer in your cryogenic, but the qubits are noisier, but then you do more error correction to compensate for this extra noise. And in some case, at the end of the day, you can gain in energy consumption. So that's a paper actually presented at the conference 2 years ago, but it's essentially how to do this. So I will go quickly on this. So it was a methodology to exactly do this kind of holistic optimization. So to essentially scale up the energy, the quantum computer really based on the physics of the qubit and to not see it as a purely engineering problem. So what we did is so it presented the method and we then applied on a highly idealized, so I insist on that, full stack model of superconducting fault-tolerant quantum computer. But essentially, the goal of the paper was really a proof of concept of scaling up quantum computer to optimize for energy efficiency by really including the physics of the qubit in the question. And what we realized is that in some example, for instance, for Shor's algorithm, if you consider a kind of engineering approach, you ignore the physics of the qubit and you scale up the computer by doing like qubit model black box, you could have a quantum computer that can consume, for instance, 10 gigawatts during an hour and a half, While if you allow yourself to open the physics of the qubit, so to incorporate it in the model, you can reduce it to 2 megawatt. And so this is, on the right, the quantum physics approach to scalability. And what is the reason here? It essentially explored the temperature trade-off I mentioned. So here, for instance, on the left, there were cold qubits, so not too much noise on the qubit, and then not a lot of error correction because the qubits are cold. But then the qubits are cold, so it costs a lot in cryogenics. And on the right, you say, okay, let's put the qubit a bit warmer, so we will have more noise. And then I compensate this noise by doing more error correction than what I would naively do. And at the end of the day, I have a bigger computer, but that ends up being more energy efficient. And that's thanks to opening the black box of the qubits physics. So to understand it differently, on the right, this approach adapts the logical and the physical gate noise, so the noise really at the hardware without error correction to minimize energy consumption. While on the left, it's a black box model, so you do not want to touch your noise of your physical qubit. And so this is why on the right you explore more scenario, so necessarily you can in general be more energy efficient. So what are the related open questions? So the first one is, even without optimizing, develop realistic full-stack energetic model of fault-tolerant quantum computer. So that's an open question, and in particular with incorporating high-rate quantum LDPC codes, and also including realistic noise model, because as I explained, you really need to understand well the noise if you want to be accurate in your energy estimate, because the reason why you spend so much energy is to fight noise. This is very important. Then an interesting question is how much energy save we could expect with such holistic approach, so scaling up the computer based on the qubits physics in now realistic architecture. And here I insisted on the qubits temperature trade-off because it's intuitive to understand, but there are many similar trade-offs you could explore. So by trade-off here, I mean you make one component more noisy, but you compensate this extra noise by, for instance, doing more error correction, or it could be also more error mitigation. And so let's give a few examples. So in error correction, you could consider less accurate error correction decoder, so the algorithm that detects and corrects error, but that consumes also less energy. So that's an example of trade-off. You could consider electronics that generates noisier signal to drive your qubit, but that then consume less energy. That's another example. And question of multiplexing can also introduce this kind of trade-off. And in particular, the two last points are interesting because actually the cost of generating the signal that will run the quantum computation could potentially cost much more than the cryogenics. And it's difficult to optimize this. And so holistic approach are a good way to tackle this problem because you can optimize this without relying on technological improvement. It's a better understanding of the full of the quantum computer at the system level. So we'll come back to it now. That's almost done for the talk. So what is the difference between reductionist and holistic optimization? So the holistic optimization, the difficulty is that they're harder to model because you really need to go down to the quantum qubits physics. You need to open this black box, and so you need a lot of interdisciplinary work. But the good thing is that they often do not require new technological development. In the sense that it's a matter of understanding how the different components of the computer interact between each other with better model, often. But reductionist optimization, I will take an example, making less consuming electronics to generate signal, often it will introduce more noise in the signal that's generated. It's difficult to reduce the consumption of the signal generation without losing in performance. But with holistic optimization, you better understand the quantum computer at the system level, and in many cases, actually, there is no need for new technological development. It's just a better understanding of the interdependencies. So that's it. We'll stop here. So there is more in the incoming paper that is here. So I will not comment on this to have a bit of time for questions. Thank you.
Great. Thank you, Marco.
Thanks. That was quite fascinating. But the question I had is somewhat related to Natalia's talk, and that is as quantum computers get bigger and bigger,
Sorry?
as quantum computers become larger, and you want to get the computation done in fixed time, we're going to need faster and faster gates. And at some point, fluctuations in the clocks will lead to errors, which would suggest you need to make the clocks better, which would require making them more dissipative. Does that figure in the ultimate limit for the thermodynamics or the energy limits for the clocks, the time, the energy required to keep the gate times accurate?
So, there are two ways to answer the question. The first one is that there is an assumption behind your question that we want to keep the same time when we scale up to larger problem, which might not necessarily be the case, but let's assume we want to do this. So then we want to have faster clock. So the thing is that before going to this fundamental limit, usually when you drive faster your qubit, you have additional noise channels that occur, for instance, leakage. So you're stuck for practical reason. But let's say we don't have this. So let's say we really want to go fast. So indeed, at some point, you might have, I think it could be actually a similar trade-off, because you would like to go, so I'm not a specialist of quantum clock, but I guess that if you want to go faster, still have a good accuracy on time, maybe indeed you will dissipate more. So it will introduce maybe more noise because of you maybe change the temperature, and you could compensate it by doing more error correction, for instance. So that's exactly a kind of loop that is in the same spirit as I presented here.
Okay, we have another.
Maria Schult had this really interesting paper, Is Quantum Advantage the Right Goal in Quantum Machine Learning? So I want to elaborate a little bit more on that. So what you call noise is that you are trying to force a quantum open system to behave like a quantum closed system. So
in some sense, yes.
Yes. So if you, let's say, enforce optimizations like this, what will be the impact on quantum complexity classes? Will we be, let's say, not be able to explore quantum complexity classes like they are exploring in this paper?
So about this paper, I'm not sure exactly, but I can understand the general spirit of your question. So for me, there is no problem of exploring more complexity classes, in the sense that there is a cost to prevent noise in the computation. The more noise you have, the more cost you have to pay. But it doesn't prevent you to, if you are ready to spend enough energy, there is no problem to reach the complexity class you want. I mean, or maybe I misunderstood what you mean, but okay, yeah.
Okay, so let's thank Marco and all the speakers of this morning.